Take a moment and contemplate a simple glass of water. It is perhaps the most familiar and the most unassuming substance in our lives. We see it as simple, as common, as a given. But in this quiet and unassuming clarity lies the most epic and the most profound story imaginable. It is a story that begins in the fiery heart of a dying star and ends with a gentle, life-sustaining sip. It is a story that connects the vast and the cosmic with the intimate and the personal. It is the story of our world. The journey we are about to embark upon is a quiet one. We will follow the path of a single, hypothetical molecule of water, from its cosmic birth to its arrival in your glass. We will witness its creation in the cold, dark nurseries of interstellar space, a marriage between the primordial hydrogen of the Big Bang and the precious stellar ash of oxygen. We will ride with it on a snowball comet as it makes its fiery and its life-giving journey to a young and a barren and a molten Earth. We will watch as it becomes a part of a great and a planet-spanning and a millions of years-long deluge, a rain that baptizes a world of fire and gives birth to the first global ocean. We will float with it in that ancient and that primordial sea, the chemical cradle where the first fragile stirrings of life began. We will see how this simple and this elegant and this polar molecule created the very conditions for our own distant and biological origin. Our journey will then join the great and the rhythmic and the planetary water cycle. We will follow our molecule as it is lifted into the sky, as it becomes a cloud, as it falls as rain. We will see it as a powerful and a geological sculptor, carving canyons and grinding down mountains over the vast and the patient expanse of deep time. We will travel with it, deep underground, through the silent and the filtering and the hidden world of aquifers. We will be drawn up into the living and the vascular and the beautiful architecture of a tree, and will be breathed out in a great and a collective and a forest-wide exhalation. And finally, our journey will intersect with the human world. We will follow our molecule as it is captured and is purified and is transported through the vast and the hidden and the modern infrastructure of our civilization. We will trace its final, quiet, and humble journey through the pipes that lie beneath our feet until it reaches its final and its most intimate destination. This is not just a story about chemistry or about geology. It is a meditation on connection. It is a quiet and a gentle and a profound reminder that the simplest things in our lives are often the most extraordinary. The water in your glass is not just water, it is stardust. It is the ghost of an ancient ocean. It is the memory of a glacier. It is the breath of a forest, and it is the lifeblood of our world. So let us begin. Let us take a slow and a deep and a meditative breath, and let us contemplate the universe in a glass. Our story does not begin on Earth. It does not begin in our solar system. It begins in a place of profound and of almost unimaginable cold and darkness and emptiness. It begins in the vast and the silent and the beautiful expanse of interstellar space, in a great and a diffuse and a ghostly object known as a giant molecular cloud. This is the birthplace of stars, and it is the birthplace of our water molecule. Let us transport our consciousness back in time and across the light years to one of these immense and cosmic nurseries. The cloud is a vast and a tenuous and a turbulent mixture of gas and dust. The gas is, overwhelmingly, the simplest and the most ancient and the most abundant element in the entire universe: hydrogen. These are the primordial hydrogen atoms that were forged in the first, few, fiery minutes after the Big Bang itself. They are the universe's primary and its most fundamental and its most ancient building block. The cloud also contains a significant amount of helium, also a product of the Big Bang. But the cloud is not made of these primordial elements alone. It has been seasoned. It has been enriched over the course of billions of years by the life and by the death of previous and of long-vanished generations of stars. The first massive stars of the universe lived fast, and they died young in spectacular and in world-changing supernova explosions. And in their fiery and their alchemical death throes, they forged the heavier elements, the elements that are the building blocks of planets and of life. They created carbon and nitrogen and silicon, and they created oxygen. Our oxygen atom, the specific and the central character in our story, was born in the heart of one of these, ancient and massive and long-dead stars. It was created in the final and the desperate and the beautiful moments of the star's life as it fused lighter elements together in a frantic and a futile attempt to hold back the inexorable and the crushing force of its own immense gravity. And when the star finally and catastrophically exploded, our oxygen atom was blasted out into the interstellar medium at a significant fraction of the speed of light. For millions, or perhaps hundreds of millions of years, our oxygen atom was a lonely and a solitary wanderer in the void. It was a tiny and an insignificant piece of stellar shrapnel, a ghost of a long-dead and a long-forgotten star. But eventually the slow and the patient and the gentle hand of gravity began to gather it, along with the primordial hydrogen gas and the dust from countless other dead stars, into the great and the cold and the dark embrace of a new giant molecular cloud. Our oxygen atom is now a part of this cloud, but it is still a free and an unattached and a solitary atom. Its story is about to take a profound and a pivotal and a beautiful turn. It is about to enter into the most important and the most enduring chemical relationship of its long and its cosmic life. It is about to participate in a cosmic marriage. Let us now zoom in to the microscopic and the almost unimaginably small scale of this cold and this dark and this prestellar environment. The temperature here is only a few tens of degrees above absolute zero, the theoretical and the physical limit of coldness. At these extreme temperatures, chemistry happens very, very slowly. The gaseous atoms are moving so sluggishly that they rarely and inefficiently interact with each other. But the cloud contains a secret, and an essential ingredient that allows this slow and this patient chemistry to happen. It contains tiny microscopic grains of dust. These dust grains, made of silicates and of carbon, are the soot of the cosmos, the condensed and the solid, remnants of the atmospheres of old and of carbon-rich stars, and they serve as the crucial and the catalytic meeting places for the atoms of the cloud. Our oxygen atom, drifting slowly and randomly through the near vacuum of the cloud, eventually collides with, and it sticks to, the cold and the frosty and the irregular surface of one of these tiny dust grains. It is now temporarily anchored. It is no longer a free-roaming particle of gas. It is part of the solid and the slowly accreting and the icy mantle of the dust grain. The surface of this dust grain is a complex and a fractal and a beautiful landscape of nooks and of crannies and of potential chemical reaction sites. And it is not an empty or a static place. It is constantly being bombarded by the other gaseous atoms and molecules in the cloud. The most common by far of these bombarding particles are the single and the highly mobile hydrogen atoms. A hydrogen atom, the smallest and the lightest and the most nimble of all the atoms, lands on the surface of the dust grain. At these incredibly low temperatures, it does not immediately and energetically bounce off. It sticks and it begins to skate or to quantum tunnel across the surface in a random and a thermal and a beautiful dance. Eventually, in its random and its microscopic wanderings, it encounters our anchored and our waiting oxygen atom. And in this quiet and this cold and this almost imperceptible encounter, a chemical reaction can occur. The oxygen atom and the hydrogen atom can form a covalent bond. They can agree to share a pair of their outer and their valence electrons. The result is a new and a highly reactive chemical species, a hydroxyl radical, OH. Our oxygen atom has entered into its first and its tentative and its chemical partnership, but the hydroxyl radical is not a stable, and it is not a fully satisfied molecule. It is still a radical, meaning it has an unpaired and a lonely electron, and it is still highly and chemically reactive. It remains anchored to the surface of the dust grain waiting. Eventually another skating and a nimble hydrogen atom will find it, and a second and a final and a consummating chemical reaction will take place. The hydroxyl radical will react with the second hydrogen atom to form a new and a now fully stable and a fully satisfied molecule. The oxygen atom now shares electrons with two separate hydrogen atoms. A molecule of H2O has been formed, a molecule of water. Let us pause and contemplate the profound and the beautiful and the almost poetic significance of this quiet and this microscopic and this cosmic event. This is a cosmic marriage. Our oxygen atom, a piece of stellar ash, a relic of a long dead and a massive star, has now been permanently and intimately and beautifully joined with two primordial hydrogen atoms, atoms that were likely born in the first, few, fiery and beautiful, minutes after the Big Bang itself. The ancient and the new have been brought together. The product of the stars has been united with the product of the very beginning of time. This single and this newly formed water molecule is a perfect and an elegant and a beautiful chemical creation. The oxygen atom is large, and it is highly electronegative, meaning it has a strong and a greedy and a powerful pull on the shared electrons. The two hydrogen atoms are small, and their single proton nuclei are left slightly and positively charged. The result is a polar molecule, a molecule with a slight negative charge on its oxygen end, and a slight positive charge on its hydrogen end. It is like a tiny and a microscopic and a chemical magnet. And it is this polarity, this uneven, and this beautiful distribution of charge that is the secret to all of water's remarkable and its unique and its life-giving properties. It is the reason that water is such an excellent and a universal solvent. It is the reason that water molecules are so strongly and so beautifully attracted to each other, forming the hydrogen bonds that give water its high surface tension, its remarkable heat-storing capacity, and its unique and its beautiful and its crystalline solid form, ice. This process of water formation is happening quietly and patiently and constantly, all over the cold and the dense and the prestellar core of the giant molecular cloud. A significant fraction of all the oxygen atoms in the cloud are being converted, in this slow and this patient and this dust-grain catalyzed chemistry, into water molecules. And these water molecules then freeze out as a thick and a frosty and an icy mantle on the surfaces of the dust grains. The cloud is becoming a vast and a cosmic and a beautiful snow globe, a vast and a cold and a dark repository of frozen and of life-giving water. Our water molecule is now a part of this vast and this cold and this beautiful and this cosmic snow globe. It is locked in a frozen and a solid and an icy state on the surface of a tiny and a microscopic dust grain. But it will not remain here forever. The slow and the patient and the gentle and the inexorable hand of gravity is at work. The giant molecular cloud is beginning to collapse under its own immense weight. A new star and a new solar system are about to be born, and our water molecule, our tiny and our precious and our well-travelled and our newly married water molecule is about to embark on the next and the most violent and the most dramatic and the most fiery chapter of its long and its beautiful and its cosmic journey. Our water molecule has been born. In a quiet and a cold and a cosmic marriage, it has been forged on the frosty surface of a microscopic dust grain, deep within the dark and the silent and the beautiful heart of a giant molecular cloud. It is now a tiny and an insignificant part of a vast and a growing reservoir of interstellar ice. But the universe is never truly static. The gentle and the patient and the inexorable hand of gravity is at work. The great and the diffuse and the cold cloud is beginning to stir. It is beginning to collapse under its own immense weight. A new star and a new solar system are about to be born, and our water molecule is about to be swept up in the great and the chaotic and the beautiful process of planetary creation. Let us watch, over the course of millions of years, as the densest and the central core of the molecular cloud collapses, faster and faster. As it collapses, it begins to spin, a consequence of the fundamental physical law of the conservation of angular momentum. The same law that causes a spinning ice skater to speed up when she pulls her arms in is now causing the collapsing prestellar core to rotate with an ever-increasing and a dizzying velocity, and as it spins, it flattens. The collapsing spherical cloud transforms into a vast and a rotating and a flattened structure. It becomes a protoplanetary disk. At the very centre of this disk, the pressure and the temperature are soaring. A new and a baby star, a protostar, is beginning to glow, a fiery and a dense and a gravitational embryo. This is the birth of our own sun. But our water molecule is not in this fiery central region. It is far out, in the cooler and the darker and the more distant reaches of the protoplanetary disk. Here, the temperature is still low enough for our water molecule to remain in its solid and its icy state, still clinging to the surface of its parent dust grain. And it is here, in this cold and this dark and this rotating disk of gas and icy dust, that the next great and creative chapter of our story begins. This is the process of accretion, the slow and the patient, and the bottom-up construction of the planets. The tiny and the microscopic dust grains, each one coated in a frosty and an icy mantle, are all orbiting the young central protostar. But their orbits are not perfectly and mathematically uniform. They jostle, they collide. And in the cold and the gentle environment of the outer disk, when they collide, they tend to stick together. This process is, at first, driven by simple electrostatic forces, the same kind of static cling that can make a balloon stick to a wall. 2 icy dust grains bump into each other, and they stay together, forming a slightly larger and a fluffier aggregate. This new larger aggregate then collides with another, and it sticks. The process continues, again and again and again. The tiny microscopic grains are slowly and patiently building up into larger and more complex and more fractal and more beautiful snowflakes. As these fluffy and these icy aggregates grow larger, from the size of snowflakes to the size of pebbles, and then to the size of boulders, a new and a more powerful force begins to take over. Gravity. An object the size of a boulder now has a significant gravitational pull of its own. It is no longer just a passive and a sticky participant in the disk. It is an active and a gravitational player. It begins to attract and to sweep up the smaller and the less massive particles in its orbital path. The process of accretion now accelerates dramatically. The rich are getting richer. The larger and the more massive objects are growing much more quickly than the smaller ones. The boulders grow into kilometer-sized objects, the planetesimals. These are the fundamental and the primary and the beautiful building blocks of the planets. Our water molecule is now a part of one of these icy and kilometer-sized planetesimals. It is a tiny and an insignificant and a frozen component of a vast and a cosmic and a beautiful snowball. It is, in essence, a comet. Let us contemplate this object. It is a loose and a porous and a dirty snowball, a mixture of water ice, of frozen carbon dioxide, of methane, and of ammonia, all held together with a matrix of the original silicate and carbonaceous dust. It is a pristine and a frozen and a beautiful sample of the original and the primordial material from which our entire solar system was formed. It is a cosmic and a chemical and a geological time capsule. For millions of years, our comet orbits the young sun in the cold and the dark and the relatively stable environment of the outer solar system. But the solar system is still a young and a chaotic and a violent place. The great and the giant and the gaseous outer planets, Jupiter and Saturn, are also forming, and their immense and their powerful gravitational influence is stirring the pot. Their orbits are migrating, and they are shifting, and they are resonating with each other in a great and a gravitational and a planetary dance. And this dance has profound and dramatic consequences for the smaller and the less massive inhabitants of the solar system, the asteroids and the comets. The gravitational influence of the giant planets acts like a great and a cosmic and a powerful slingshot. It flings the small and the icy and the rocky bodies of the solar system into new and highly elliptical and highly chaotic orbits. This is the beginning of a period known, with a beautiful and a dramatic and a simple clarity, as the late heavy bombardment. It is a period about 4.1 to 3.8 billion years ago when the inner solar system was subjected to a furious and a cataclysmic and a constant rain of impacting asteroids and comets. Our comet, the cosmic and the dirty snowball that contains our water molecule, is caught up in this great and this gravitational and this chaotic upheaval. Its stable and its circular and its distant orbit is perturbed. It is sent on a new and a long and an arcing and an inward trajectory. It is falling towards the sun. As it travels from the cold and the dark and the distant outer reaches of the solar system into the warmer and the brighter and the more central regions, it begins to change. The heat from the young sun begins to warm its icy and its frosty surface. The frozen and the ancient ices begin to sublimate, to turn directly from a solid into a gas. A beautiful and a ghostly and a temporary atmosphere, a coma, begins to form around the solid nucleus of the comet, and the solar wind, the constant and the tenuous and the powerful stream of charged particles that is flowing out from the young sun begins to push on this coma, blowing it out into a long and a beautiful and a diaphanous and a glowing tail. Our comet has grown its iconic and its beautiful and its transient and its cosmic hair. But its destination is not the sun itself. Its new and its chaotic and its elliptical orbit happens to intersect with the orbit of a young and a still forming and a barren and a fiery and a rocky planet. The third planet from the sun, the Earth, the final and the most violent and the most dramatic and the most creative chapter of our water molecule's cosmic journey is about to take place. The comet is on a collision course. To contemplate the journey of the comet is to appreciate the chaotic and the violent and the beautiful and the creative nature of planetary formation. It is to understand that our solar system was not born in a state of quiet and of orderly and of mathematical perfection. It was born in a state of chaos and of violence and of constant and of cataclysmic collision. And it is to understand that the water on our planet, the precious and the life-giving and the beautiful, water that fills our oceans and that makes up our own bodies, is not truly native to our world. The Earth was formed in the hot and the dry and the inner part of the solar system, a region where the water ice could not easily and stably condense. Our water is an import, it is a gift. It is a delivery from the outer and the colder and the more distant and the more ancient reaches of our own solar system. It is a gift from the comets. Our water molecule, after its long and its cold and its beautiful and its cosmic journey, is finally and violently and beautifully coming home. The final and the most violent and the most creative act of our water molecule's cosmic journey is at hand. The dirty and the cosmic and the beautiful snowball, the comet that has been its home for millions of years, is now hurtling on a collision course through the inner solar system. Its target is a young and a barren and a fiery and a still-forming world. Its target is the Hadean Earth. Let us try to imagine the scene on this young and this hellish and this almost unrecognizable planet, some 4.5 billion years ago. The Earth is a world of rock and fire. It is a world that is still reeling from the immense and the cataclysmic and the planet-forming impact that created its own moon. The surface is a global and a molten and a glowing magma ocean, a sea of liquid rock that is kept in its molten state by the constant and the violent rain of impacting planetesimals and by the intense and the decaying heat of the short-lived radioactive elements in its core. The sky, if one could call it that, is a dark and a dusty and an oppressive orange, filled with the smoke and the ash and the sulphurous gases of countless and of constant volcanic eruptions. There is no solid ground, there are no oceans, and there is no breathable air. It is a world that is, in every conceivable sense of the word, a hell. Into this fiery and this chaotic and this primordial scene, our comet arrives. It streaks through the thin and the tenuous and the carbon dioxide-rich atmosphere, a brilliant and a fleeting and a final flash of cosmic light. And then it strikes. The impact is an event of almost unimaginable and of almost incomprehensible violence. The immense and the kinetic energy of the comet, an object that is several kilometers in diameter and is travelling at a speed of tens of thousands of kilometers per hour, is converted in a single and a blinding and an instantaneous flash into heat. The comet itself, and a large and a significant portion of the Earth's molten and its rocky crust that it strikes, are vaporized. A crater, hundreds of kilometers in diameter, is blasted into the surface of the magma ocean. A plume of superheated and of vaporized rock and gas is ejected high into the atmosphere and even into space itself. Our water molecule, which was, a moment ago, a stable and a frozen and a solid, part of the comet's icy nucleus, is now subjected to this immense and this instantaneous and this violent release of energy. It is torn apart. The strong and the covalent, bonds that have held it together since its birth in the cold, interstellar cloud are, for a brief and a fiery and a violent moment, broken. Its constituent oxygen and hydrogen atoms are dissociated, and they become part of the expanding and the superheated and the plasma-like fireball of the impact. But as this fireball expands, and as it cools, the atoms quickly and eagerly recombine. Our water molecule is reformed, but it is no longer a solid. It is no longer a part of a frozen and an icy and a cosmic snowball. It is now a gas. It is a molecule of water vapor, of steam. And this steam is blasted high into the young and the tenuous and the hot terrestrial atmosphere. And it is not alone. It joins a vast and a growing and an almost unbelievable amount of other gaseous water that is being delivered by the constant and the furious and the cataclysmic rain of countless other impacting comets and water-rich asteroids. And it also joins the vast and the significant amount of water that is being outgassed from the planet's own hot and its molten and its volcanic interior. The young Earth's atmosphere is becoming incredibly and almost unimaginably and powerfully humid. It is a thick and a dense and a suffocating and a crushing blanket of steam mixed with the other volcanic gases like carbon dioxide and nitrogen and sulfur dioxide. The atmospheric pressure at the surface is immense, perhaps hundreds of times what it is today, and the temperature is scorching, hot enough to melt lead and to keep the very surface of the planet in a molten and a liquid and a fiery state. The Earth is now a giant and a planetary scale and a beautiful and a terrible pressure cooker. The thick and the water vapor-rich atmosphere acts as a powerful and an insulating greenhouse blanket, trapping the heat from the molten magma ocean and from the constant and the fiery and the cosmic bombardment. The surface remains a sea of liquid rock, far too hot for the water to condense into a liquid. For millions, or perhaps even tens of millions of years, this state of affairs persists. The Earth is a world of steam and rock. Our water molecule spends this long and this fiery and this turbulent period of its life as a tiny and an insignificant and a ghostly part of this vast and this chaotic and this superheated steam atmosphere. But slowly and patiently and inexorably things begin to change. The great and the cosmic and the chaotic dance of the planets begins to settle down. The solar system is slowly and gradually cleaning up its remaining and its orbital and its construction debris. The rate of the late heavy bombardment, the constant and the violent and the fiery rain of impacting comets and asteroids begins to decrease, and at the same time the short-lived and the highly radioactive elements in the Earth's interior are decaying away, reducing the planet's own internal and its powerful heat production. The Earth is beginning to cool. As the planet cools, it reaches a critical and a beautiful and a world-changing threshold. The surface temperature of the magma ocean finally drops below the boiling point of water at the immense and the crushing and the atmospheric pressures of the time. The molten and the liquid rock begins to solidify. A thin and a dark and a fragile and a black and a basaltic crust begins to form on the surface of the planet. It is a crust that is constantly being shattered and being recycled by the impacts of the remaining large asteroids and being torn apart by the powerful and the convective currents in the hot and the plastic mantle beneath it. But it is a beginning. The Earth, for the very first time in its long and its fiery and its violent history, has a solid surface. And now a new and an even more dramatic and a more beautiful and a more life-giving transformation can begin. As the atmosphere continues to cool, it reaches the dew point, the vast and the almost unbelievable and the planet-spanning amount of water vapor that is held in the thick and the dense and the heavy atmosphere can now begin to condense into liquid water droplets. The first, and the tentative and the beautiful, clouds begin to form in the upper and the cooler and the rarefied layers of the terrestrial atmosphere, and then it begins to rain. This is not a rain that we can easily or that we can comfortably imagine. It is a global, and it is a torrential, and it is a relentless, and it is a planet-forming downpour. It is a rain of hot and of acidic and of mineral-rich water falling from a dark and an oppressive and a heavy sky of steam onto a black and a barren and a volcanic and a newly solidified landscape. It is a rain that may have lasted for millions of uninterrupted years. It is the great and the primordial and the beautiful and the planetary deluge. Our water molecule, which has been a part of the hot and the turbulent and the gaseous steam atmosphere for so long, is now caught up in this great and this global and this beautiful condensation event. It becomes part of a liquid and a hot and a heavy water droplet, and it falls out of the sky and onto the surface of the young and the cooling and the waiting Earth. As the great and the relentless and the global rain falls, it cools the surface, allowing more and more of the fragile and the black and the basaltic crust to solidify, and it begins to fill the low-lying and the vast and the numerous impact basins and the great and the volcanic and the tectonic depressions. The first and the shallow and the hot and the acidic and the beautiful seas begin to form, and as the rain continues and continues and continues, these seas grow deeper and they grow wider and they merge until they form a single and a vast and a beautiful and a planet-spanning global ocean. The young Earth has been transformed. The world of steam and rock has become a water world. The sky has cleared. The thick and the heavy and the oppressive steam atmosphere has collapsed out of the sky and into a liquid and a beautiful and a global ocean, leaving behind a thinner and a much more transparent and a much more recognizable atmosphere of nitrogen and carbon dioxide. The surface of the planet is now, for the very first time, a place of relative and of quiet and of beautiful calm. Our water molecule is now a part of this new and this global and this beautiful and this life-giving ocean. It is a tiny and an insignificant drop in a vast and a planetary scale and a beautiful body of water. It is a world that is still profoundly and deeply alien to us. The water is hot. It is acidic. The skies are pale and a hazy and an orange-pink under a faint and a young and a distant sun, and there is no free oxygen to breathe. But the stage is now set. The environment has been created. The great and the chemical and the beautiful and the planetary laboratory of the primordial ocean is now finally open for business. The great and the planet-forming and the millions of years-long deluge is over. The thick and the heavy and the oppressive steam atmosphere has collapsed out of the sky and has been transformed into a vast and a beautiful and a planet-spanning global ocean. The young Earth is now a water world. Our water molecule, after its fiery and its violent and its atmospheric sojourn, is now floating, peacefully, in this new and this immense and this planetary body of water. It has found a home. But this is not a quiet, or a static, or an inert home. The primordial ocean is a dynamic and a reactive and a chemically transformative place. It is the great and the planetary and the chemical laboratory where the next and the most profound and the most mysterious chapter in our planet's story is about to be written. And the key to this great and this creative and this chemical potential lies in the unique and the beautiful and the almost magical properties of the water molecule itself. It lies in water's remarkable and its unparalleled ability to act as the universal solvent. Let us return for a moment to the fundamental and the beautiful and the chemical nature of our water molecule. It is a simple and an elegant and a three-atom structure, a single, large, oxygen atom bound to two, smaller hydrogen atoms. But the arrangement of these atoms is not symmetrical. The molecule is bent into a wide V shape, with the oxygen atom at the vertex, and the oxygen atom is highly electronegative. It is a chemical and an electron and a subatomic bully. It has a powerful and a greedy and an insatiable pull on the electrons that it is supposed to be sharing with the two hydrogen atoms in their covalent bonds. The result of this uneven and this beautiful and this subatomic tug-of-war is that the shared electrons spend much more of their time orbiting the large oxygen nucleus than they do orbiting the small hydrogen nuclei. This creates a slight but a significant separation of charge across the molecule. The oxygen end of the molecule acquires a persistent and a slight negative charge, delta minus, while the two hydrogen ends acquire a persistent and a slight positive charge, delta plus. The water molecule is polar. It is a tiny and a microscopic and a chemical magnet with a distinct and a permanent positive and negative pole. And it is this simple and this beautiful and this fundamental polarity that is the secret to almost all of water's remarkable and its life-giving and its world-changing properties. It is the reason that water is such an extraordinary and such a powerful solvent. Let us now contemplate the scene in the primordial terrestrial ocean. Our water molecule is surrounded by billions and by trillions of other identical water molecules. And because they are all tiny, and they are all polar, and they are all microscopic, magnets, they are all powerfully and beautifully attracted to each other. The positive hydrogen end of one water molecule is strongly attracted to the negative oxygen end of a neighbouring water molecule. This attraction is called a hydrogen bond. These hydrogen bonds are not as strong as the covalent bonds that hold the water molecule itself together. They are weaker, and they are more transient, and they are constantly and beautifully breaking and reforming in a fluid and a dynamic and a microscopic dance. But they are strong enough, and they are numerous enough to give liquid water its remarkable and its unique and its cohesive properties. It is the hydrogen bonds that are responsible for water's high surface tension, its ability to stick to itself and to form a skin on its surface. And it is the hydrogen bonds that give water its incredibly high heat capacity, its ability to absorb and to store and to transport vast amounts of thermal energy, which helps to moderate the planet's climate. But the true and the creative and the chemical power of water's polarity is revealed when other substances are introduced into this cohesive and this hydrogen bonded and this beautiful network. The primordial ocean is not made of pure H2O. It is in constant and it is in intimate contact with the two other great and chemical reservoirs of the young, Earth, the volcanic and the rocky, crust below it, and the carbon dioxide rich and the nitrogen rich atmosphere above it. The hot and the acidic and the mineral rich rain that formed the oceans has already begun the process of chemical and of geological weathering. And the constant and the powerful and the hydrothermal activity on the ocean floor, the black smokers and the volcanic vents, are spewing a rich and a complex and a beautiful cocktail of dissolved minerals and gases directly into the deep ocean water. Let us consider what happens when a simple and a common and a crystalline salt like sodium chloride NaCl is introduced into the water. The salt crystal is held together by ionic bonds, the strong and the electrostatic, attraction between the positively charged sodium ions Na+, and the negatively charged chloride ions Cl-. But when this crystal is placed in water, the tiny and the numerous and the polar water molecules go to work. The negative, oxygen ends of the water molecules are strongly attracted to the positive, sodium ions in the crystal lattice, and the positive, hydrogen ends of the water molecules are strongly attracted to the negative chloride ions. The water molecules surround the ions, they mob them, they form a hydration shell around each individual ion, insulating it from its oppositely charged neighbours in the crystal. The collective and the cumulative and the beautiful pull of these millions of tiny and microscopic and chemical magnets is stronger than the ionic bonds that are holding the crystal together. The crystal dissolves. The sodium and the chloride ions are pulled apart and they are held in solution, each one surrounded by its own personal and its beautiful and its watery and its hydration shell entourage. This is the simple and the beautiful and the profound power of water as a solvent. It is able to dismantle and to dissolve and to hold in solution a vast and a diverse and a beautiful array of ionic and polar substances. The primordial ocean is, therefore, becoming a rich and a complex and a beautiful and a chemical soup. It is a solution that is rich in dissolved salts, like sodium and potassium and calcium and magnesium. It is rich in dissolved gases, like carbon dioxide and nitrogen and methane and ammonia, which have dissolved directly from the atmosphere into the surface waters, and it is rich in the dissolved and the mineral and the elemental building blocks of life, the phosphates and the sulfates and the trace metals that have been leached from the rocks and have been spewed from the hydrothermal vents. Our water molecule is now a part of this rich and this complex and this beautiful and this life-giving and this chemical soup. It is the medium. It is the matrix. It is the universal solvent that is bringing all of these different and these disparate and these essential chemical ingredients together in one vast and planetary scale and beautiful and chemical laboratory. It is in this watery and this chemical and this beautiful soup that the first and the most important and the most mysterious and the most beautiful chemical reactions of prebiotic chemistry can begin to take place. The dissolved and the simple and the inorganic molecules can begin to interact and to react and to form larger and more complex and more interesting organic molecules. The energy for these reactions is coming from the lightning in the atmosphere, from the intense ultraviolet radiation from the young sun, as there is not yet an ozone layer to block it, and from the intense and the chemical and the thermal energy of the deep sea hydrothermal vents. Amino acids, the building blocks of proteins, are being formed. Nucleotides, the building blocks of RNA and DNA, are being formed. Simple sugars and lipids are being formed. The primordial ocean is becoming a rich and a complex and a beautiful and a self-organizing and a chemical and a creative cauldron of possibility. And water is not just the passive and the inert and the background solvent for these reactions. It is an active and a crucial and a chemical participant. In many of these prebiotic chemical reactions, water molecules are themselves consumed in hydrolysis reactions or are produced in dehydration or condensation reactions. Water is both the stage and one of the primary actors in this great and this chemical and this creative drama. To contemplate the primordial ocean is to appreciate the profound and the beautiful and the creative power of water as a solvent. It is to see how this simple and this bent and this polar molecule has the ability to break down the solid and the mineral world and to transform it into a fluid and a dynamic and a reactive and a chemical and a life-giving and a beautiful and a planetary and a creative medium. It is the universal solvent that dissolves the boundary between geology and biology, between the non-living and the living. It is the womb of all possibility, the cradle in which the first and the most fragile and the most beautiful stirrings of life on our planet will soon begin to awaken. Our water molecule, having journeyed from the heart of a star and across the cosmic void, now finds itself an anonymous participant in the greatest of all planetary dramas, the origin of life. It is part of a vast global ocean, a restless and chemically rich environment that covers the young Earth. This is not the tranquil blue sea we know today. It is a warmer, more acidic and more dynamic world, relentlessly churning under a sky thick with volcanic gases and a sun that shines with a fainter, younger light. It is within this primordial cauldron, this universal solvent, that the very definition of existence is about to be rewritten. The story of life's beginning is inextricably bound to the story of water, for it was not just a backdrop for this event, but the active medium, the facilitator, and the protector of the first fragile steps toward biological complexity. To understand water's role as the cradle of life, we must first appreciate its fundamental, almost magical chemical nature. Our molecule, H2O, is deceptively simple in its structure but possesses a suite of properties that make it uniquely suited for nurturing life. It is a polar molecule with a slight positive charge on its hydrogen atoms and a slight negative charge on its oxygen atom. This polarity turns each water molecule into a tiny magnet, allowing it to form weak hydrogen bonds with its neighbours. This sociability is the secret to its power. It is this very property that allows water to dissolve more substances than any other liquid, earning it the name the universal solvent. In the primordial ocean, our molecule and its countless brethren were tirelessly at work, pulling ions from the volcanic rock of the seafloor, dissolving salts, and holding a rich brew of minerals and gases in suspension. This created the legendary primordial soup, a complex aqueous solution of carbon compounds, minerals, and other chemicals, energized by lightning strikes, volcanic heat from hydrothermal vents, and the unfiltered ultraviolet radiation from the young sun. Within this dynamic chemical broth, the building blocks of life, amino acids, nucleotides, and lipids, could form, accumulate, and most importantly, interact. Without water to bring these components together, they would have remained isolated and inert. Water was the ultimate matchmaker, creating a planetary-scale laboratory where the chemistry of life could begin. Beyond its role as a solvent, water provided the stable and protective environment that the first delicate biological structures desperately needed. Life, in its earliest forms, was an incredibly fragile affair. The transition from a collection of non-living organic molecules to a self-replicating system is a monumental leap, one that requires a specific set of physical conditions. Water's high heat capacity was paramount. The young Earth was a planet of extremes, with intense volcanic activity and a fluctuating climate. The oceans, however, could absorb and store immense amounts of heat energy without a drastic change in their own temperature. Our water molecule, by vibrating and forming and breaking hydrogen bonds with its neighbours, helped to buffer the primordial soup from these violent thermal swings. This thermal stability created a predictable and gentle environment where complex molecules like RNA and proteins could fold into stable, functional shapes without being immediately denatured by a sudden spike in heat. A puddle might evaporate or freeze, but the vastness of the ocean provided a persistent, stable sanctuary. Furthermore, water offered a physical shield. The surface of the early Earth was bombarded by intense ultraviolet UV radiation from the sun, as the protective ozone layer had not yet formed. This high-energy radiation is lethal to complex organic molecules, capable of shattering their delicate chemical bonds. By simply being submerged, even a few meters below the surface, the first protocells were shielded from the worst of this radiation. Our water molecule, along with the layers of its kin above it, absorbed and scattered the deadly UV rays, creating a safe zone in the depths. This is why many scientists believe life may have originated not in shallow surface pools, but in the deeper, darker, and more protected environments around. Hydrothermal vents on the ocean floor. Here, the chemical-rich plumes erupting from the Earth's crust provided both the raw materials and the energy for life, all while the water column above provided a steadfast shield against the harsh realities of the surface world. The physical properties of water also facilitated the very structure of life. The first cells needed a boundary, a membrane to separate their internal chemistry from the external environment. These membranes are primarily composed of lipids, molecules that have a dual nature, a head that is attracted to water, hydrophilic, and a tail that is repelled by it, hydrophobic. When placed in water, these lipids spontaneously arrange themselves into a belayer, with their water-loving heads facing outward towards the ocean and inward towards the cell's interior, while their water-fearing tails tuck themselves away in the middle. This structure, the lipid bilayer, is the basis of all cellular membranes today. It was water's inherent polarity and its interaction with these lipids that drove the automatic self-assembly of the first cellular containers. Our water molecule, by simply being itself, nudged and organized these lipids into spheres, creating the first enclosures, the first insides and outsides, the first sacred spaces where the chemistry of life could be concentrated and controlled. Inside these newly formed protocells, water continued its essential work, now as a transport medium. The interior of a cell, the cytoplasm, is itself a complex aqueous solution. Nutrients, waste products, proteins, and genetic material are all ferried around the cell, suspended or dissolved in water. Our molecule became part of this internal ocean, a microscopic courier facilitating the constant flow of materials and information that defines a living system. It participated directly in countless biochemical reactions, a process called hydrolysis, where a water molecule is used to break down larger molecules, releasing energy or creating smaller building blocks. Conversely, it was expelled during dehydration synthesis, where smaller molecules are joined together to build the complex polymers of life, like proteins and DNA. Water was not just the stage, it was an active participant in the play, its atoms being incorporated into and released from the very molecules of life itself. As we contemplate our single water molecule, adrift in this primordial sea, we see it not as a passive observer, but as an essential catalyst. It was the medium that gathered the ingredients, the shield that protected them, the thermostat that stabilized their environment, and the architect that helped construct their containers. It was the solvent, the stabilizer, and the transport system. Every property that makes water so familiar to us, its wetness, its ability to dissolve sugar in our tea, its slowness to boil, was a critical factor in allowing non-life to cross the threshold into life. The first cell was, in essence, a captured droplet of the ocean, a tiny self-contained world that had learned to manage its own internal sea. The story of life's origin is a testament to a profound partnership, a co-evolution between chemistry and its environment. The cradle of life was not just in water. In many ways, the cradle was water. Our molecule, forged in a star and delivered by a comet, had found its ultimate purpose: to serve as the gentle, life-giving medium from which all biology on Earth would spring. Its journey was far from over, but its most creative act was now complete. Life had begun. For eons, our water molecule has been a constituent of the vast, singular body of the primordial ocean. It has been a witness to the birth of life, a participant in the slow, simmering chemistry that allowed the first cells to form and flourish in the deep. But life, once sparked, is a dynamic force. The emergence of photosynthesis in early microorganisms like cyanobacteria began to fundamentally re-engineer the planet. These tiny life forms, using sunlight as their energy source, started to release a waste product that would change the world forever: oxygen. As oxygen filled the atmosphere, it created the ozone layer, diminishing the harsh UV radiation at the surface. The world was becoming a more hospitable place, and the stage was set for the next great act in our molecule's journey. It was time for it to leave the ocean, to take to the sky, and to become part of a planetary-scale engine that would distribute life across the globe, the Great Water Cycle. The journey begins with a moment of profound transformation, powered by the faint but persistent energy of the young sun. Our water molecule, floating near the ocean's surface, absorbs a photon of light. This single packet of solar energy is enough to excite it, causing it to vibrate more rapidly and increasing the kinetic energy it possesses. It jostles against its neighbours, the hydrogen bonds that have held it captive in the liquid ocean for so long, stretching and straining. With one final burst of energy, the bonds break. Our molecule is liberated. It sheds the collective embrace of the liquid and ascends, now as an invisible vapour, into the atmosphere. This is evaporation, the first step in the cycle, a silent, constant exodus of water from the surface to the sky. It is an act of levitation on a global scale, lifting trillions of tons of water every second, turning the oceans into an enormous sun-powered engine. As our molecule rises, it enters a completely different realm. The atmosphere is a vast, chaotic ocean of air, a turbulent mix of gases where temperature and pressure change dramatically with altitude. Carried upward on a thermal current, a rising column of warm, moist air, our molecule travels higher and higher. The world below, the endless expanse of the ocean, shrinks to a blue curve. Up here, the temperature plummets. The cold of the upper atmosphere saps the energy from our molecule, slowing its frantic vibrations. This loss of energy makes it less solitary, more inclined to seek companionship. It encounters a microscopic speck, a particle of volcanic ash, sea salt, or cosmic dust, known as a cloud condensation nucleus. This tiny particle acts as a gathering point, a microscopic stage for the next transformation. Drawn to this nucleus, our now lethargic water molecule collides with it and sticks. It has found an anchor. Soon, another water vapor molecule joins it, and then another, and another. This is condensation, the magical process where invisible gas transforms into a visible liquid. A microscopic droplet is born, a speck of liquid water suspended in the sky, with our molecule at its heart. Billions upon billions of other molecules are undergoing the same process all around it, clustering onto countless other nuclei. Together, these droplets form a vast, visible community, a cloud. Our molecule is now part of a castle in the air, a floating testament to the water cycle's power. From the ground, a cloud appears solid and soft, but from within, it is a swirling, dynamic environment of suspended water droplets and ice crystals, a world of its own drifting on the high-altitude winds. Being part of a cloud is a journey in itself. Our molecule is carried across the sky by global wind patterns, which act as the planet's great atmospheric rivers. It may travel for hundreds or thousands of miles, passing over the ocean, and, for the first time, over the barren, rocky land masses of the early continents. The cloud is a transport system, taking the water evaporated from the ocean and carrying it inland to regions that would otherwise remain parched and lifeless. This distribution is the water cycle's most critical function. It is the mechanism by which the planet shares its most precious resource, preventing the oceans from having a monopoly on water and life. Within the cloud, our molecule's journey is far from static. It may be jostled by turbulence, pushed upward into colder regions where it freezes into a tiny ice crystal, its structure shifting from the fluid chaos of a liquid to the beautiful hexagonal symmetry of ice. It might then fall, melt back into a droplet, and be swept upward again in a cycle of freezing and thawing within the cloud. During this time, its droplet grows. It collides and merges with other droplets in a process called coalescence. As it grows larger and heavier, the upward air currents that once held it aloft begin to fail. Gravity, the ever-present force that our molecule defied during evaporation, begins to reassert its dominance. The moment of return arrives. The droplet, now heavy enough to overcome the updrafts, begins to fall. This is precipitation. Our molecule, as part of this falling drop of rain, descends from the sky. Its journey down is a sensory experience. It rushes through the air, the world growing larger and more detailed below. After its ethereal existence in the cloud, it is now on a direct and determined course back to the surface. It falls onto a sun-baked volcanic rock on a desolate, lifeless continent. For the first time in its long existence, our molecule rests on land. This single drop of rain, joined by countless others, marks a pivotal moment. The baptism of the continents has begun. On the surface, the journey continues. This is the collection phase of the cycle. Our raindrop joins with others, and the power of their collective mass begins to show. They form a tiny rivulet seeking the path of least resistance, flowing into cracks and crevices in the rock. This is surface runoff. The rivulet merges with others to form a stream, and the stream joins others to form the first primordial river. This river, driven by gravity, carves a path through the landscape, beginning the slow, patient work of erosion that will shape the face of the planet. Our molecule is now an agent of geological change, a tiny particle in a powerful current that grinds down rock, transports sediment, and begins to sculpt the valleys and canyons that will define the continents for billions of years to come. Alternatively, our molecule's journey could take a quieter, more hidden path. Instead of flowing over the surface, the raindrop might seep into the ground, a process called infiltration. It trickles down through porous soil and fractured rock, pulled deeper by gravity. It leaves the world of light and air behind and enters the subterranean realm of groundwater. Here, it may join a vast, slow-moving underground river or become part of an aquifer, a massive reservoir of water held in layers of rock and sand. This hidden journey is a slow and patient one. Our molecule might remain underground for days, years, or even millennia, filtered and purified by its passage through the earth. This underground water is not stagnant. It flows, albeit incredibly slowly, often eventually emerging back at the surface in a spring, or seeping directly into a riverbed or the ocean, completing its cycle in silence and darkness. Whether by the dramatic rush of a river or the slow creep of groundwater, the ultimate destination is the same. The river our molecule is part of flows inexorably downward, finally reaching the coast and pouring back into the vastness of the ocean. Our molecule is home. It has completed one full turn of the great water cycle. It was lifted by the sun, carried by the wind, fell as rain, and flowed back to its source. This entire journey, evaporation, condensation, precipitation, and collection, is the planet's beating heart, a rhythmic, cyclical pulse that has been beating for billions of years. This cycle is the engine of climate and the circulatory system of the biosphere. It moderates the planet's temperature by moving heat from the equator to the poles. It weathers rock, releasing essential minerals that nourish life. Most importantly, it delivers fresh water to the land, allowing life to conquer the continents. The first, plants that colonized the land could only do so because the water cycle provided them with the rain they needed to survive. The forests, the grasslands, the animals, every form of terrestrial life owes its existence to this continuous, planet-spanning system of water delivery. Our molecule will not rest. It will make this journey again and again, in countless variations. It may be evaporated from a leaf in a process called transpiration, be locked in a glacier for 10,000 years, or be drunk by an animal and become part of its body for a short while. But eventually it will always return to the cycle, as we contemplate our molecule, now once again part of the ocean, waiting for the sun's energy to lift it back into the sky. We understand that the water cycle is more than a physical process. It is a story of connection, of renewal, and of the profound and enduring link between the sky, the land, and the sea. It is the Earth's eternal promise that life, no matter where it is, will be sustained. The planet's heart continues to beat. Our water molecule has now completed its first turn of the great water cycle. It has known the freedom of the open sky and the communal embrace of the cloud, has fallen as life-giving rain upon barren land, and has journeyed back to the ocean through the planet's nascent arteries. In this rhythmic exchange between sea, sky, and land, our molecule is no longer just a passive component of the environment. It has become an active agent of change. As the continents, pushed by the slow, inexorable forces of plate tectonics, continue to rise and drift, water becomes the primary tool of planetary artistry. The story of the landscape, of every mountain, valley, canyon, and coastline, is a story written by water. Our molecule is now a sculptor, and its chisel is time itself. The process begins with the simplest of acts, the impact of a single raindrop. As our molecule, part of a falling drop, strikes the surface of a rock, it transfers a minuscule amount of kinetic energy. One drop does nothing, but 1,000,000 drops, 1,000,000,000 drops, falling over 1,000 years, is a force of immense power. This is the beginning of weathering. Water, the universal solvent, goes to work. Rainwater is naturally slightly acidic because it dissolves carbon dioxide from the atmosphere, forming weak carbonic acid. As our molecule seeps into the microscopic cracks and fissures of the rock, this acid begins to dissolve the mineral bonds that hold the rock together. It is a slow chemical siege, patiently breaking down the integrity of even the hardest granite. Feldspar turns to soft clay, and other minerals are carried away in solution. This is chemical weathering, the silent molecular-level deconstruction of the Earth's crust. The physical power of water is even more dramatic. In colder regions or at higher altitudes, our molecule participates in a powerful geological process known as frost wedging. It seeps into a crack in a rock as liquid, water. As night falls and the temperature drops below freezing, our molecule arranges itself into the crystalline lattice of ice. In this transformation, it expands by about 9%, exerting a tremendous outward pressure on the surrounding rock. It acts like a tiny silent jackhammer, widening the crack from within. When the sun returns, the ice melts, and our molecule, now liquid again, seeps even deeper into the newly widened fissure. The next night, it freezes again, expanding and pushing the crack further apart. Night after night, season after season, this relentless cycle of freezing and thawing pries the rock apart. A tiny crack becomes a fissure, and eventually a large boulder can be split from a cliff face, all through the patient, expansive power of frozen water. Once the rock is broken, water's role shifts from demolition to transportation. Our molecule, now part of a sheet of rainwater flowing over a hillside, picks up a tiny grain of sand, a fragment of rock liberated by weathering. This is erosion. The water itself is an abrasive force, but its true power comes from the sediment it carries. The stream our molecule has joined is now a moving belt of liquid sandpaper. The particles of sand, silt, and gravel, carried in the current, scour the streambed, deepening the channel. The river becomes a liquid file, grinding away at the landscape. Boulders, tumbled along the riverbed during floods, act as giant grinding tools, smashing against the bedrock and breaking off more fragments. Our molecule is part of a slurry, a dynamic mixture of water and rock that is actively carving the earth. We follow our molecule as it joins a young, energetic river high in a newly formed mountain range. The slope is steep, and the water flows with incredible speed and force. Here, the river's primary job is to cut downward. It carves a deep V-shaped valley, its path dictated by the underlying geology, but its progress driven by the relentless energy of flowing water. Our molecule rushes through turbulent rapids, swirls in powerful eddies, and plunges over waterfalls, each movement contributing to the excavation of the landscape. A waterfall is a place of intense erosion, as the falling water undercuts the rock ledge, causing it to collapse and the waterfall to slowly retreat upstream, leaving a gorge in its wake. The Grand Canyon is perhaps the most awe-inspiring testament to this power, a colossal chasm carved over millions of years by the steady, sediment-laden flow of the Colorado River. Our single molecule participating in this flow is part of the grand geological force that carved such a masterpiece. As the river leaves the mountains and flows onto a flatter plain, its energy decreases. The slope is gentler, and the river slows down. It can no longer carry the heaviest of its sediment load. Boulders and gravel are the first to be abandoned, deposited on the riverbed. The river's erosional focus shifts from cutting downward to cutting, sideways. It begins to meander, swinging back and forth across its floodplain in wide, looping curves. On the outside of a bend, the water flows faster, eroding the bank and widening the loop. On the inside of the bend, the water is slower, and it deposits sediment, building up a point bar. Our molecule might be part of the fast-moving current that eats away at a cliff, or part of the slow-moving water that lays down a new layer of sand. Over centuries, these meanders migrate across the valley floor, constantly reshaping the landscape. Occasionally, during a great flood, the river will cut a new, shorter channel, abandoning a meander loop which becomes a serene, crescent-shaped oxbow lake. Finally, the river approaches its end. As it meets the still water of a lake or the ocean, its velocity drops to almost zero. It can no longer hold on to its sediment. In this final act of surrender, it deposits everything it has carried. The sand, silt, and clay settle out, building a delta, a fan-shaped landform created from the transported remains of the mountains. Our molecule, its long journey of erosion and transportation complete, flows out into the ocean, leaving behind the sediment it has carried for hundreds of miles. The delta of the Mississippi, the Nile, or the Ganges are vast, fertile plains built entirely from rock that was weathered and eroded far upstream, a testament to the cumulative work of countless water molecules over millennia. The mountains are, quite literally, being delivered to the sea, one grain of sand at a time. Water's sculptural power is not limited to rivers. On the coastlines, the ocean itself is a relentless artist. Our molecule, now part of a wave, is lifted by the wind's energy far out at sea. As the wave approaches the shore, it begins to drag on the shallowing seafloor, slowing down and growing in height until it breaks in a crash of foam and energy. This constant battery of waves against a coastline is a formidable erosional force. Waves smash against cliffs, compressing air in cracks with explosive force, a process called hydraulic action. They also hurl pebbles and sand against the rock, abrading it like a sandblaster. Our molecule is part of this chaotic, energetic assault, chipping away at the land's edge. Softer rock is eroded more quickly, forming bays, while harder rock is left behind as dramatic headlands. Over time, waves can carve sea caves, arches, and eventually, isolated sea stacks, lonely pillars of rock that stand as monuments to the land that once surrounded them. But water is not only a force of destruction, it is also a builder of coastlines. The same waves that erode the headlands carry the sediment along the shore in a process called longshore drift. This sediment is deposited in quieter waters, building up sandy beaches, spits, and barrier islands. A beach is not a static feature. It is a river of sand constantly in motion, supplied, shaped, and moved by the action of water. Our molecule, in the gentle lapping of a wave, might deliver a grain of sand to a beach, helping to build and replenish this fragile, dynamic boundary between land and sea. In this chapter of its existence, our water molecule has been a tireless worker, an agent of entropy and creation. It has participated in the chemical decay of rock, the physical shattering of stone by ice, the grinding of canyons by rivers, and the shaping of coastlines by waves. It has demonstrated the profound geological principle that soft, flowing water, given enough time, can overcome the hardest of rock. The landscapes of our planet, which seem so permanent and solid to our fleeting human perception, are in fact dynamic and fluid, constantly being sculpted by the patient, persistent and powerful hand of water. Our molecule, whether rushing in a mountain torrent or gently lapping on a sandy shore, is part of this grand geological artistry, a slow sculptor working on a planetary canvas, turning mountains into sand and carving the very face of the earth. Our water molecule's journey has been one of ceaseless motion. It has known the turbulent energy of a mountain river, the slow, meandering grace of a lowland stream, and the rhythmic pulse of an ocean wave. It has been an agent of change, a sculptor of continents, and a courier of life-giving rain. Now, its journey takes a turn towards stillness. Carried by atmospheric currents to the coldest regions of our planet, Our molecule is about to enter a state of suspended animation, a long, frozen slumber where it will become part of one of Earth's most extraordinary features, a glacier. In this frozen state, it will not be an active sculptor but a passive recorder, a tiny fragment of a vast crystalline library that holds the secrets of the planet's past. The journey begins, as always, with a fall from the sky, but this time it is not as rain. High in the polar regions or at the summit of a towering mountain range, the air is so cold that our water molecule does not condense into a liquid droplet. Instead, it undergoes deposition, transforming directly from an invisible gas into a solid. It crystallizes around a nucleus, not into a simple frozen drop, but into an intricate six-sided flake of snow. This is a moment of perfect symmetry, a fleeting masterpiece of physics. Our molecule becomes one arm of a delicate dendrite, a star-shaped crystal that is unique in its pattern, yet obedient to the fundamental hexagonal geometry of water ice. Joined by trillions of others, it falls in a silent, gentle flurry, blanketing the stark, frozen landscape below. It lands on a vast, pre-existing field of snow, a place where the accumulation of winter snow exceeds the melting of summer. This is the accumulation zone of a glacier. The snowflake our molecule is part of is light and airy, full of empty space, but it does not remain so for long. As new layers of snow fall on top of it, the pressure begins to mount. The delicate, feathery arms of the snowflake are broken and compressed. The snowpack begins a slow transformation. The initial fluffy snow is compacted into a granular, denser form called firn. It is no longer a collection of individual snowflakes, but a mass of interconnected ice grains. Our molecule is now part of this transitional substance, buried deeper and deeper with each passing season, the memory of its perfect crystalline form lost to the immense weight from above. The pressure continues to increase. As hundreds, then thousands of feet of snow and firn accumulate, the pressure becomes so great that it squeezes out the last remaining pockets of air between the ice grains. The firn recrystallizes, its grains growing larger and interlocking into a solid, dense mass of ice. This is glacial ice. It is a profound transformation. Our molecule, once a floating snowflake, is now locked into a solid, blue-tinted matrix. The air that was trapped between the original snow crystals is now encased within the ice as tiny, pressurized bubbles. Our molecule is now part of a glacier, a river of ice, and locked beside it is a tiny, pristine sample of the ancient atmosphere from the year it fell as snow. Life within the glacier is a study in slow, immense motion. A glacier is not a static block of ice. It is a fluid, albeit one that moves on a geological timescale. Driven by its own colossal weight, the glacier begins to flow downhill or outward from its center. Our molecule, buried deep within the ice, moves with it. This movement is not a smooth glide. The ice deforms under the pressure, a process called plastic flow. Layers of ice crystals slide past one another, and individual crystals stretch and change shape. The journey is incredibly slow, a few inches, perhaps a few feet, per day. Our molecule, locked in its icy prison, may take thousands or even tens of thousands of years to travel from the accumulation zone to the glacier's edge. It is a journey of immense patience, a slow-motion pilgrimage across the frozen landscape. As part of this flowing river of ice, our molecule is once again an agent of geological change, but in a new and far more powerful way. At the base of the glacier, the ice grinds against the bedrock with unimaginable force. The glacier plucks huge boulders from the ground, freezing onto them and carrying them along. These trapped rocks act as giant cutting tools, gouging and scraping the bedrock below, carving long striations that will remain as scars on the landscape for millennia, a clear signpost of the glacier's passage. The glacier does not carve a V-shaped valley like a river. Its immense, widespread power scours the landscape, creating a broad, U-shaped valley. It bulldozes hills, carves deep basins that will later become lakes, known as tarns, and sharpens mountain peaks into jagged horns and arêtes. Our molecule, deep within the ice, is part of this colossal engine of erosion, a slow-motion cataclysm that completely reshapes continents. But the true significance of our molecule's time in the glacier is not the work it does, but the record it keeps. The glacier is a frozen archive, a library of climate history written in layers of ice. Each year, a new layer of snow is added, and each layer is different. A warmer year might produce a thicker layer, a colder year, a thinner one. A major volcanic eruption somewhere on the planet will spew ash into the atmosphere, which will travel globally and be deposited as a dark, dusty layer within the ice, a clear marker in the geological record. Our molecule is part of one specific layer, a single page in this vast frozen book. The tiny air bubbles trapped alongside our molecule are the most precious text in this library. These bubbles are time capsules containing actual physical samples of Earth's past atmosphere. By drilling deep into the ice sheets of Antarctica and Greenland, scientists can extract ice cores, long cylinders of ice that can stretch back hundreds of thousands of years. By carefully melting a section of the core in a vacuum, they can analyze the ancient air trapped within. They can measure the concentration of greenhouse gases like carbon dioxide and methane, and from this, they can reconstruct past climates with astonishing accuracy. They can see the regular rhythm of the ice ages, the planet's slow breathing in and out over millennia. Our molecule, resting in its layer, is a silent witness to this history. The ice around it holds the story of the climate, the atmosphere, and the major environmental events of the era in which it fell. The chemistry of our water molecule itself is also a source of information. Water molecules are not all identical. Some, a very small fraction, contain heavier isotopes of hydrogen, deuterium, or oxygen, oxygen-18. It takes more energy to evaporate these heavier water molecules from the ocean. Therefore, the temperature of the atmosphere determines the ratio of heavy to light isotopes in the snow that falls. In colder periods, there are far fewer heavy isotopes in the precipitation. By measuring the isotopic ratio of the ice in each layer of an ice core, scientists can create a precise thermometer of Earth's past. The layer containing our molecule has a specific isotopic signature, a chemical fingerprint that records the average global temperature of its time. For millennia, our molecule remains in this state of suspended animation, part of a slow, grinding journey. It travels from the high interior of the ice sheet toward the coast. Finally, it approaches the glacier's edge, the ablation zone, where the ice is lost faster than it accumulates. Here, its long slumber comes to an end. The glacier may terminate in the ocean, where our molecule's journey could end dramatically. It reaches the calving front, the cliff face of ice where the glacier meets the sea. Immense cracks, or crevasses, form as the ice stretches and breaks. A colossal block of ice, weighing millions of tons, detaches from the glacier and crashes into the sea. Our molecule is part of this new iceberg. As an iceberg, it has a final ghostly journey. It floats away on the ocean currents, a majestic melting mountain of ancient ice. It is a piece of the past, adrift in the present. It carries with it the cold of the poles, chilling the water and air around it. As it drifts into warmer latitudes, it begins to melt. The ancient ice, compressed for millennia, fizzes and pops as the pressurized air bubbles from a bygone era are finally released. It is the sound of the past escaping into the present. Our molecule, locked away for so long, is finally liberated. The ice that held it dissolves, and it is released back into the liquid ocean, the very ocean from which it was evaporated tens of thousands of years ago. Its return to the sea is a profound moment. It has been absent from the liquid world for an entire geological epoch. While it was frozen, mountains may have risen, continents may have drifted, and entire species may have evolved and gone extinct. It returns to a world that may be subtly or dramatically different from the one it left. By rejoining the ocean, it brings with it the chemical signature of its time, a whisper of the past climate. And the story it helped to preserve, locked in the ice cores, allows a new intelligent species, humans, to read the planet's history, to understand the forces that govern our climate, and to see our own place within the long, epic story of the Earth. Our molecule's time as a frozen archivist is over. It is once again a part of the dynamic, flowing world, ready for the next chapter in its endless journey. Our water molecule has experienced the world in its most dramatic forms. It has been part of the violent energy of a river carving a canyon, the majestic, slow-motion force of a glacier grinding down a mountain, and the chaotic crash of a wave against a cliff. It has known the sunlit surface of the ocean and the ethereal heights of the atmosphere. Now its journey takes it away from the light, away from the grand, visible spectacles of planetary change and into the quiet, hidden world beneath our feet. Its next chapter is one of stealth and patience, a slow, filtering pilgrimage through the pores and cracks of the Earth itself. This is the story of groundwater. The journey begins not with a dramatic rush, but with a quiet act of disappearance. Our molecule, having returned to the ocean from a melting iceberg, once again evaporates, condenses into a cloud, and falls as rain. This time it lands on a gentle forested slope, a landscape covered in a thick blanket of soil, rich with decaying leaves and tangled with the roots of ancient trees. Instead of rushing over the surface to form a stream, the raindrop is absorbed. It disappears. This is infiltration, the process by which surface water begins its descent into the earth. The first part of this underground journey is through the soil zone. Our molecule trickles past, grains of sand, clumps of clay, and fragments of organic matter. This is a world teeming with unseen life. It slips past the burrow of an earthworm, is brushed by the delicate, questing tip of a plant root, and flows around colonies of microscopic bacteria and fungi. This top layer of the earth is a natural filter. As our molecule percolates downward, the soil strips away impurities, dust particles, and microbes. The journey is slow, governed by the pull of gravity and the intricate labyrinthine pathways of the soil structure. It is a descent into darkness, leaving the world of weather, seasons, and sunlight behind. After passing through the soil, our molecule reaches a region called the unsaturated zone, or vadose zone. Here, the pores in the rock and sediment are filled with a mixture of air and water. Our molecule is not part of a flowing body of water, but rather clings to the surfaces of rock particles as a thin film, a state known as vadose water. It continues its slow, downward creep pulled by gravity, moving from one particle to the next. This phase of the journey can be incredibly slow, a creeping descent that can take days, weeks, or even years to travel just a few meters. It is a time of profound quiet and isolation, a stark contrast to the communal, dynamic existence in a river or a cloud. Eventually, our molecule trickles down far enough to reach a significant boundary, the water table. This is not a hard line, but the upper level of a region where all the pores and fractures in the rock are completely filled with water. This is the saturated zone. As our molecule crosses this threshold, it leaves the last pockets of air behind and becomes once again part of a collective body of water. It has arrived in an aquifer. An aquifer is not an underground lake or cavern in the way one might imagine. It is a layer of porous rock like sandstone or loose material like gravel or sand that is saturated with water and can transmit it in usable quantities. Our molecule has effectively entered a hidden subterranean river, one that flows not through an open channel, but through the countless interconnected pores of the rock itself. Life in the aquifer is a world of immense pressure and perpetual darkness. The weight of the rock and water above is immense. The temperature is nearly constant, reflecting the average annual temperature of the surface far above, insulated from the daily or seasonal fluctuations of the outside world. The flow is, by all human standards, incredibly slow. While a surface river might flow at several miles per hour, the water in an aquifer might move only a few feet per year, or in some cases a few inches per century. Our molecule is now part of this slow, creeping flow, a nearly imperceptible migration through the rock. Its journey is no longer measured by the sun or the seasons, but by geological time. The aquifer is a vast and complex system. Our molecule might travel through a layer of porous sandstone, its journey a slow filter through the tiny spaces between sand grains that were themselves deposited by an ancient river millions of years ago. Or it might find itself in a limestone aquifer, a rock formed from the fossilized shells of ancient sea creatures. Here, the journey can be more dramatic. Over eons, the slightly acidic nature of the water has dissolved the limestone, creating a network of underground channels, conduits, and vast caverns. This is a karst landscape. In this environment, our molecule's journey might speed up, flowing through a hidden river in a lightless cave, passing by fantastic formations of stalactites and stalagmites, calcium carbonate deposits left behind by eons of dripping water. It might become part of a vast, silent underground lake, a body of water that has not seen the sun in millennia. During this long subterranean journey, our molecule's relationship with the rock is intimate. It continues the work of chemical weathering, dissolving minerals from the surrounding rock and carrying them in solution. This is how groundwater becomes hard, rich in dissolved calcium and magnesium. The water is being chemically imprinted by its journey, its composition becoming a unique signature of the geological strata it has passed through. This slow, filtering passage also provides an incredible degree of purification. The rock acts as a microfine filter, removing any remaining impurities, making the water exceptionally clean. This ancient filtered water is some of the purest on the planet. The water in these deep aquifers can be incredibly old. Our molecule might remain underground for thousands, or even hundreds of thousands of years. This is fossil water, a non-renewable resource that was deposited during a previous geological era, perhaps during an ice age when rainfall patterns were different. It is a relic of a past climate preserved in the deep earth. By being part of this ancient water, our molecule is a link to a world that no longer exists. But no matter how long it remains underground, the journey of groundwater is still part of the Great Water Cycle. The vast majority of groundwater is in constant, albeit slow motion, and it is always heading toward a point of discharge. After its long, slow journey through the darkness, our molecule approaches the surface once more. It may emerge at a spring, a place where the water table naturally intersects with the ground surface. Here, it bubbles up out of the ground, clear, cold, and pure, forming a pool that gives birth to a new stream. It is a moment of rebirth, as our molecule re-enters the sunlit world, its long, quiet pilgrimage complete. Alternatively, it might discharge directly into a river or a lake. Many rivers, especially during dry periods, are fed not by surface runoff, but by the steady, invisible seepage of groundwater from their banks and bed. This is called base flow, and it is what keeps rivers flowing long after the last rain has fallen. Our molecule could seep silently into the bottom of a river, joining the faster-moving surface water and being carried once more toward the sea. In other cases, it might emerge directly into the ocean. Along many coastlines, there are submarine groundwater discharge points, where fresh water from terrestrial aquifers flows out from the seafloor. Here, our molecule would emerge into the salt water, a plume of fresh, cold water creating a unique, localized ecosystem on the ocean floor before mixing back into the vastness of the sea. This hidden world of groundwater is of immense importance to the planet and to humanity. Aquifers are the largest accessible reservoir of fresh water on Earth, dwarfing the amount of water in all the rivers and lakes combined. They are a vital buffer, storing water from wet years and releasing it slowly during dry years, sustaining ecosystems and providing a reliable source of water for human use. For much of human history, we have tapped into this hidden resource through wells, drawing up this naturally filtered water for drinking and agriculture. As we contemplate our molecule's journey through the deep earth, we gain an appreciation for the unseen systems that support our world. We understand that the landscape is not just a surface, but a complex three-dimensional structure with a hidden circulatory system of its own. This journey through the underground is one of purification, patience, and profound slowness. It is a chapter defined not by energy and action, but by quietude and persistence. Having been cleansed and aged by its long passage through the rock, our molecule emerges back into the light, ready for its next adventure, carrying with it the mineral memory of its deep, dark, and silent journey. Our water molecule has journeyed through the non-living world, through rock and river, ice and air. It has been an agent of geology, a sculptor of stone, and a keeper of ancient climate records. Now, its path converges with the world of biology in the most intimate way possible. After emerging from the darkness of an aquifer into the light of a forest spring, it has trickled into the soil, a medium now rich with the promise of life. Here, it will be summoned to participate in one of nature's most elegant and silent miracles, the life of a plant. Its next journey is an upward one, a silent vertical ascent against the pull of gravity, inside the vascular system of a great tree. The journey begins with a subtle invitation. Our molecule, percolating through the moist soil near the forest floor, drifts close to a root hair, a microscopic single-celled extension of a tree's root system. The tree, a towering oak that has stood for centuries, is a vast living entity, and its roots form an immense intricate network, a mirror image of the branches above, constantly exploring the soil for water and nutrients. The The cells within the root are saltier. They have a higher concentration of solutes than the water in the soil. This simple difference in concentration creates an osmotic potential. Driven by this fundamental force of physics, our water molecule is drawn across the semi-permeable membrane of the root hair. It passes from the outside world into the living tissue of the tree. This is not a violent or energetic process. It is a quiet, passive diffusion, a gentle summons to cross the threshold from the mineral world into the biological one. Once inside the root, our molecule is no longer a solitary traveller. It has entered the plant's circulatory system. It moves from cell to cell, or through the porous cell walls, making its way toward the central core of the root. Here, it enters a specialized tissue, a bundle of microscopic pipes called the xylem. The xylem is the tree's primary water-conducting system, a marvel of natural engineering. It is a continuous network of hollow, dead cells, joined end to end, forming unbroken tubes that run from the deepest root tip, up through the entire length of the trunk and branches, and out to the smallest vein in the highest leaf. Our molecule has just stepped onto a biological superhighway, a silent, upward-flowing river. The ascent begins. The question of how a tall tree lifts water hundreds of feet into the air without a mechanical pump is a question that has fascinated scientists for centuries. The answer lies in a beautiful, coordinated effort of physics and biology. The process is not pushed from below, it is pulled from above. Far up in the canopy, hundreds of feet away, the leaves of the tree are releasing water vapor into the atmosphere, a process we will soon explore called transpiration. As a water molecule evaporates from a leaf, it creates a tension, a negative pressure, in the xylem. Because water molecules are polar and stick together so effectively, a property called cohesion, this pull is transmitted all the way down the continuous column of water in the xylem. It is like pulling on a rope. The evaporation of one molecule from a leaf tugs on the molecule next to it, which tugs on the one next to it, and so on, creating a continuous chain of tension that reaches all the way down to the roots. Our molecule, now in the xylem of the root, feels this gentle but inexorable pull. It is drawn upward, joining the silent ascending stream. This is the cohesion tension theory, the beating heart of plant hydraulics. The journey is a smooth, steady flow. Our molecule travels up through the woody tissue of the root into the massive trunk of the oak. It is now inside one of the countless xylem vessels that, bundled together, form the sapwood, the living, water-conducting portion of the tree's trunk. It is moving through a world of wood, a complex and beautiful architecture of cellulose and lignin, flowing through pipes that are narrower than a human hair. The journey is completely silent and effortless. There is no heart to pump, no muscle to contract. The entire process is powered passively by the sun's energy, evaporating water from the leaves far above. Our molecule is part of a living river, flowing upward at a speed that can range from a few inches to several feet per hour, depending on the time of day, the humidity, and the thirst of the tree. It flows past the records of the tree's own history, the annual growth rings that mark the passing of seasons and years, each ring a testament to the water that flowed in seasons past. As it ascends, our molecule is not just a passenger, it is a vital courier. Dissolved within the water of the xylem are the essential minerals and nutrients that the roots have absorbed from the soil: nitrates, phosphates, potassium, and magnesium. Our molecule is part of the solvent that carries these raw materials of life upward, delivering them to the cells of the trunk, the branches, and the leaves, where they will be used to build new tissues, to fuel metabolism, and to sustain the life of the tree. The water itself is also a critical ingredient. It fills the plant's cells, creating turgor pressure, the internal hydrostatic pressure that keeps the plant rigid and upright. A plant that lacks water wilts, its cells losing this internal pressure. Our molecule, by being part of this internal hydraulic system, is literally helping the tree to stand tall and reach for the sun. The journey continues, up the main trunk and then into a major branch that arches out toward the open sky. The xylem tubes begin to divide and subdivide, becoming narrower and more numerous, branching out like a fractal pattern. Our molecule follows one of these paths, moving out along the branch, then into a smaller twig, and finally into the petiole, the small stalk that connects a single leaf to the twig. It has now travelled hundreds of feet from the dark soil, and it is about to enter the tree's primary solar panel and food factory, a leaf. It flows into the leaf's intricate network of veins, which spread out across the blade of the leaf, ensuring that every cell is just a short distance from a water supply. The journey is almost at its end. Our molecule is drawn out of the xylem and into the cells of the leaf's interior, the mesophyll. This is where the magic of photosynthesis happens. The leaf is alive with activity. Chloroplasts are busy capturing sunlight, using its energy to split other water molecules, a process called photolysis, and combine carbon dioxide from the air with hydrogen to create sugars, the food that powers the entire tree. Our molecule is not split for photosynthesis, but its presence is essential. It keeps the leaf cells turgid and functional, and it replenishes the water that is constantly being lost to the air. The final stage of its journey within the tree is its arrival at the surface of a mesophyll cell deep inside the leaf. Here it coats the cell wall, which is adjacent to an airspace within the leaf's porous interior. The air inside the leaf is saturated with water vapor, but the air outside the leaf is usually drier. This difference in humidity creates a water potential gradient. The end of the line is a tiny pore on the underside of the leaf called a stoma, plural stomata. These stomata are the tree's mouths, opening to take in carbon dioxide for photosynthesis and, as an unavoidable consequence, releasing water vapor. Our molecule on the surface of the mesophyll cell feels the pull of the drier air. It transitions one last time, from a liquid to a gas. It evaporates from the cell wall into the airspace within the leaf. It has become water vapor. As a gas, it diffuses through the airspace and out through an open stoma. It has left the tree. It is back in the open atmosphere. This process, the release of water vapor from a plant's leaves, is transpiration. Our molecule's journey inside the tree from root hair to leaf pore may have taken only a few hours, but it was a journey of profound significance. It was part of the transpiration stream, the living river that is the lifeblood of the plant. This stream connects the soil to the atmosphere, acting as the planet's green circulatory system. It cools the plant, delivers essential nutrients, and maintains the hydraulic pressure that supports its structure. Our molecule was a tiny essential part of this system. It was a building block, a coolant, and a courier. By participating in this silent, upward-flowing river, it enabled a towering oak to reach for the sky, to create food from sunlight, and to breathe life into the landscape. It has now been offered back to the sky, ready to form a cloud and continue its journey, leaving behind a living, breathing monument to its passage. Our water molecule has just completed an extraordinary journey, an upward climb against gravity through the silent, living architecture of a great oak tree. It has been drawn from the soil, transported through a network of microscopic pipes, and used to sustain the very life of the tree. Now its journey takes another pivotal turn. Having been released from the surface of a leaf through the invisible pore of a stoma, it has been given back to the atmosphere. It is no longer an individual molecule of water vapor, but a participant in a collective phenomenon of immense scale and power, the breath of a forest. This chapter is a contemplation of that collective release, a process that transforms landscapes, shapes weather, and reveals the forest as a singular, unified entity that actively engineers its own environment. The moment of departure is a quiet transition. Our molecule, having evaporated from the moist surface of a leaf cell, diffuses as a gas into the open air. It is now free from the biological machinery of the tree, floating in the thin, relatively still layer of air that clings to the leaf surface, known as the boundary layer. But it is not alone. All around it, from the millions of other stomata on the same leaf, and from the countless leaves on the same tree, a steady, invisible stream of water vapor is emerging. And this tree is just one of billions in the vast forest. Our molecule has joined an immense, silent, upward-flowing river of vapor, a river that is rising from the entire forest canopy. This is transpiration on a massive scale. We pull our perspective back, viewing the forest not as a collection of individual trees, but as a single, superorganism. From this vantage point, the entire forest canopy is a vast living surface area, exquisitely designed for gas exchange. The combined surface area of all the leaves in a forest is many times greater than the ground area the forest covers. This enormous surface is constantly exhaling water vapor. A single, large oak tree, like the one our molecule just departed from, can transpire over 100 gallons of water on a hot, dry day. A full acre of forest can release thousands of gallons. The Amazon rainforest, the largest on Earth, releases an estimated 20 billion tons of water into the atmosphere every single day, a volume greater than the discharge of the Amazon River itself. Our molecule is a tiny, indistinguishable part of this staggering quantity of water, the collective breath of the green world. This massive release of water vapour has a profound and immediate effect on the local environment. The process of evaporation requires energy, which is drawn from the leaf and the surrounding air in the form of heat. This is why transpiration is often called plant sweat. It is a vital cooling mechanism for the plant, preventing its leaves from overheating in direct sunlight. But on a larger scale, the collective transpiration of the forest acts as a giant natural air conditioner. The air within and immediately above the forest is significantly cooler and more humid than the air over an adjacent open field or a city. Our molecule, as it rises, is part of this bubble of cool, moist air, a localized climate created entirely by the biological activity of the forest. It is a testament to the power of life to regulate its own conditions. As our molecule rises further, carried upward on thermal currents generated by the sun-warmed canopy, it becomes part of a larger atmospheric story. The vast plume of moisture rising from the forest is, in essence, creating its own weather. As this warm, humid air rises, it expands and cools, just as it did when it evaporated from the ocean. The cooling reduces the air's capacity to hold water vapour. Our molecule, once again, slows down and seeks a nucleus, a microscopic particle of dust, pollen, or even volatile organic compounds released by the trees themselves. It condenses, forming a liquid water droplet. It has become part of a cloud. But this is a special kind of cloud. Unlike clouds that form over the ocean, this one was born directly from the breath of the forest. It is a biological cloud. Scientists have discovered that forests are not just passive sources of moisture, they actively seed their own clouds. The volatile organic compounds VOCs released by trees, the chemicals that give a forest its characteristic fresh, piney or earthy smell, can react in the atmosphere to form tiny aerosol particles that are exceptionally effective as cloud condensation nuclei. The forest, in a way, is exhaling both the water and the very seeds upon which that water can condense. It is a self-perpetuating system. Our molecule, now part of a newly formed cloud directly over the forest, is part of a positive feedback loop. The white, puffy cumulus cloud it has helped to form reflects sunlight back into space, which helps to keep the forest below cool. More importantly, this cloud will eventually grow heavy enough to produce rain. And this rain will fall back down upon the forest that generated it. This is precipitation recycling. A water molecule can be transpired from a leaf, form a cloud, fall as rain, be absorbed by a root, and be transpired again, all within the same forest ecosystem, sometimes in a matter of days. In large, dense forests like the Amazon, it is estimated that a single water molecule may be recycled 5 to 6 times before it finally leaves the basin and returns to the ocean. This concept of the forest breathing and creating its own rain has led to the biotic pump theory. This theory proposes that the intense transpiration of large forests creates a persistent low-pressure zone over the land. The massive condensation of water vapour into clouds releases latent heat, causing the air to rise and further lowering the surface pressure. This low pressure acts like a giant vacuum cleaner, actively drawing in moist air from the ocean. According to this theory, it is not the wind that brings the rain to the forest, but the forest that summons the wind and the rain to it. The forest is the heart of a continental-scale hydraulic engine, its collective breath creating an atmospheric river that flows from the ocean deep into the interior of the continent, sustaining the entire ecosystem. Our molecule, whether rising from a leaf or being drawn in from the sea, is part of this vast, life-driven weather machine. We can contemplate the journey of our molecule from this new perspective. It fell as rain, was drawn into a tree, and was then transpired back into the atmosphere. In doing so, it contributed to the humidity, the cooling, and the cloud formation that will bring the next rain. It is a participant in a system of profound cooperation. Every tree in the forest, by transpiring, is contributing to the atmospheric moisture that will sustain its neighbours. It is an act of unconscious collective altruism, a system where the survival of the individual is inextricably linked to the health of the whole. The influence of this forest breath extends beyond just creating local rain. The patterns of transpiration affect global weather systems. The moisture released by the great forests of the Amazon, the Congo, and Southeast Asia is transported by atmospheric currents around the world, providing rainfall to distant agricultural regions. The health of these forests is therefore linked to the food security of populations thousands of miles away. The breath of the Amazon can influence rainfall in the American Midwest. The breath of the Congo Basin can affect the monsoons in Asia. Our molecule, rising from a single leaf, has become a player on the global stage, a tiny part of a biological process with planetary consequences. As our molecule drifts in the cloud above the canopy, it has a moment of stillness, a chance to be a part of the sky that the forest itself has created. Below, the canopy stretches out like a green ocean, a textured, living sea of the leaves. The air is filled with the sounds of the forest, the buzz of insects, the call of birds, the rustle of leaves, sounds that are all dependent on the very cycle our molecule is part of. The forest is a complete, self-sustaining world, and its breath is the engine that drives it. This chapter of our molecule's journey is a revelation. It shows that the division between the living and non-living world is not as clear as it seems. Life is not just a passive recipient of the environment's conditions, it is an active creator of those conditions. The forest breathes, and in doing so it makes the world habitable for itself. It is a profound demonstration of the interconnectedness of the Earth's systems, where the smallest biological process, the opening of a stoma on a single leaf, can, when multiplied by billions, alter the climate of a continent. Our molecule, by passing through the body of a tree and being returned to the sky, has not just completed a step in the water cycle. It has been an integral part of a declaration of life's power to shape a planet. It now waits in its biologically formed cloud, ready for the next turn of the wheel, ready to fall again as rain, a gift from the forest to itself. Our water molecule has been on a journey of ceaseless transformation. It has been a component of rock, a force of erosion, a prisoner in ice, and the lifeblood of a tree. Most recently it was exhaled by a forest, an invisible speck of vapour rising on a current of air, a single note in the great green breath of the biosphere. Now its journey enters a phase of ethereal beauty and quiet contemplation. It has become part of a cloud. This chapter is a meditation on that existence, a departure from the world of action and consequence into a realm of pure form, light, and ephemeral stillness. It is an exploration of the cloud not as a meteorological phenomenon, but as a place, a transient kingdom in the sky. The transition was a moment of quiet magic. As the warm, moist air from the forest rose, it cooled. The frantic, energetic dance of our water molecule as a gas began to slow. The invisible became visible. Drawn by an infinitesimal electrostatic charge, it found its anchor, a microscopic particle of pollen, a speck of dust, or a crystal of sea salt that had journeyed far from the ocean. This is the moment of condensation. Our molecule sheds its energetic freedom and clings to this nucleus, becoming a liquid once more. It is no longer alone. All around it, in the same instant, countless other water molecules are making the same transition, each finding its own nucleus. A microscopic droplet is born, and our molecule is an indistinguishable part of it. This droplet, 1,000 times smaller than a grain of sand, is so light that the slightest updraft keeps it suspended. A mote of liquid dust floating in the vastness of the sky. This single droplet is nothing, but it is joined by 1 trillion others, and together they are everything. They are a cloud. Our molecule is now a citizen of this floating metropolis, a castle in the air. From the ground, a cloud appears as a solid, billowy object, a piece of tangible fluff adrift in the blue. But from within, it is a world of immense space and subtle substance. It is a near vacuum, a swirling diaphanous mist where the distance between droplets is vast compared to their size. To be inside a cloud is to be in a fog, a world where visibility is reduced to a few feet, where light is diffused into a soft, omnidirectional glow, and where the only sound is the whisper of the wind. Our molecule drifts in this luminous, silent space, a tiny point of liquid in a universe of air. The cloud has an architecture, a life cycle of its own. The one our molecule has joined is a cumulus humilis, a fair-weather cloud. It is born from a rising thermal of warm air, its flat base marking the precise altitude where the air has cooled to the dew point, and condensation begins. Its top is a billowing cauliflower-like dome, the visible manifestation of the rising turbulent air within it. Our molecule is caught in this gentle internal circulation. It is lifted in the updraft at the cloud's center, rising toward the sunlit upper towers, and then sinks slowly down the cooler, clearer edges, sometimes even evaporating back into invisible vapor for a moment, before being drawn back into the fold. It is a slow, churning dance, a gentle ride on a celestial carousel. Life in the cloud is a continuous play of light. Sunlight streaming from above enters the cloud and is transformed. As a ray of light strikes the droplet containing our molecule, it is scattered. The droplet acts as a tiny prism and a lens. The light ray is bent or refracted as it enters the water, reflects off the back surface of the droplet, and is refracted again as it exits. Because all the colours of the spectrum are scattered more or less equally, the light that emerges is a brilliant, pure white. This is why clouds are white. They are not coloured objects. They are colossal chandeliers, scattering sunlight in all directions. Our molecule is part of this grand illumination, a tiny, perfect sphere participating in the diffusion of daylight, turning the harsh glare of the sun into the soft, gentle light of an overcast day. Sometimes, under the right conditions, a more spectacular optical effect occurs. If the sun is directly behind the observer's point of view, the light entering the droplet containing our molecule can be refracted and reflected in such a way that it exits back toward the sun, split into its constituent colours. When this happens in millions of droplets at once, it creates a rainbow. To be in a cloud when a rainbow is formed is to be at the very source of colour, to see the world through a prism of pure light. At other times, as light passes through a cloud composed of uniform droplets, it can be diffracted, creating an iridescent glow around the sun or moon, a phenomenon called a corona, a soft, pastel-hued halo. Our molecule, in its simple, spherical droplet, becomes a key player in these beautiful, fleeting atmospheric artworks. The cloud is also a place of constant change, a battleground of competing forces. Gravity pulls relentlessly on the droplet containing our molecule, urging it downward. But the updraft of rising air pushes it back up. It is held in a state of delicate equilibrium, a perfect balance between the upward push of thermal energy and the downward pull of planetary mass. The cloud exists only as long as this balance is maintained. It is a standing wave in the river of the atmosphere, a form that persists even as the individual water molecules that compose it are constantly changing. Our molecule may only spend a few hours in this particular cloud before it evaporates or falls as rain, but the cloud itself may endure, constantly replenishing its substance with new vapour from below. As our molecule drifts, it may witness the cloud's evolution. If the atmospheric conditions are right and the updrafts are strong, the small cumulus cloud can grow, building upon itself, rising higher and higher into the colder reaches of the atmosphere. It becomes a cumulus congestus, a towering, muscular cloud, its top boiling with energy. Inside, the motion is more violent. Our molecule is swept upward at great speed into regions where the temperature is well below freezing. Here, a new transformation occurs. The liquid droplet it is part of does not necessarily freeze immediately. It can become supercooled, remaining liquid far below its freezing point, a state of fragile instability. Then, it might collide with a tiny ice crystal or a freezing nucleus. The shock of this collision causes the entire supercooled droplet to flash freeze in an instant. Our molecule is now part of a solid particle of ice. It might grow larger as it collides with other supercooled droplets, which freeze onto its surface, a process called accretion. This is how hailstones are born. Our molecule could be trapped in the heart of a piece of ice, cycled repeatedly up and down within the cloud, growing larger with each ascent, until it is heavy enough to plummet to the earth. But today, the atmosphere is stable. The cloud does not grow into a storm, it remains a gentle, drifting castle. Our molecule, in its liquid droplet, floats in the quiet upper portions of the cloud. From this vantage point, it has a perspective few ever experience. Below, the earth is a patchwork of green forests, brown fields, and the dark, shimmering blue of a lake. The world of gravity, of solid ground and rooted things, seems distant and abstract. Up here, in the kingdom of the air, the rules are different. The landscape is one of vapour and light. Other clouds drift by like silent ships, each a unique sculpture, shaped by the invisible currents of the wind. There are the thin, wispy cirrus clouds, high-altitude streaks of pure ice crystals that are the frozen breath of the upper troposphere. there are the vast, sheet-like stratus clouds, which form in stable, layered air and can create a uniform grey ceiling that covers the entire sky. To be a cloud is to be a boundary. It is the edge between the visible and the invisible, the line between the humid air below and the drier air above. It is a physical manifestation of a thermodynamic threshold. Our molecule, sitting at this boundary, is part of the Earth's process of self-regulation. Clouds play a critical role in the planet's energy balance. Their white tops reflect incoming solar radiation back to space, exerting a cooling effect. At the same time, they can trap outgoing infrared radiation from the Earth's surface, acting like a blanket and exerting a warming effect. The net result of these two opposing forces is one of the biggest uncertainties in climate science, and our molecule is on the front line of this global energy budget. For now, these global implications are far away. The reality for our molecule is one of quiet suspension. It has no goal, no destination. It simply is. It is part of a form that is the very definition of impermanence. A cloud is a shape, not a thing. It is a process, not an object. It is a momentary pattern created by the flow of energy and matter through the atmosphere. To contemplate the journey of our molecule is to understand this. It has been part of a mountain, which seems permanent, but is slowly eroding to nothing. It has been part of a tree, which seems static but is a dynamic river of life. And now it is part of a cloud, the most honest of all forms, a beautiful transient castle in the air that makes no pretense of permanence. It is a reminder that the entire world, and everything in it, is in a state of constant graceful flux. The cloud drifts, the light shifts, and our molecule waits for the gentle pull of gravity to begin the next chapter of its story, the return to Earth. Our water molecule has been living an ethereal existence, a resident of a floating sunlit castle in the air. As part of a cloud, it has known a state of near-perfect equilibrium, held aloft by rising currents, a participant in the sky's silent, luminous artistry. But this state of suspension is, by its very nature, temporary. The cloud is a way station, not a final destination. The inexorable pull of gravity, a force our molecule has defied since its evaporation, begins to reassert its claim. The time has come for the return journey. This chapter is about that descent, the transformation from a suspended droplet to a falling raindrop, and the profound significance of its arrival on the land below. This is the story of the gentle rain. The process begins with a subtle shift in the cloud's internal dynamics. The gentle updrafts that have kept the cloud afloat begin to wane, or the process of droplet growth accelerates. Our molecule is part of a tiny cloud droplet, one among trillions. On its own, it is far too light to fall. It needs to grow. This happens through a process called collision and coalescence. The cloud is a turbulent place, and as our droplet is jostled by air currents, it collides with other, smaller droplets. Due to surface tension, when they touch, they merge, forming a single, larger droplet. Our molecule is now part of a slightly bigger collective. This process repeats itself again and again. The droplet eats its smaller neighbours, growing in size and mass with each collision. It takes about 1 million cloud droplets to coalesce into a single raindrop. It is a process of aggregation, of community building on a microscopic scale. As the droplet containing our molecule grows, its relationship with the air changes. It becomes heavier, and its terminal velocity, the constant speed it reaches when the downward pull of gravity is balanced by the upward push of air resistance, increases. It begins to fall relative to the smaller droplets around it, allowing it to sweep up even more of them on its way down. The descent has begun. It is no longer a suspended cloud droplet, but a committed raindrop. Our molecule leaves the bright sunlit top of the cloud and begins its fall through the cloud's body. The world inside the cloud, once a place of soft, diffused light, becomes progressively darker as it descends through the dense, misty layers. Finally, it emerges from the flat, grey base of the cloud. It has left the castle in the air and is now falling through the open sky. The journey to the ground has truly begun. As it falls, the raindrop takes on its characteristic shape. Small raindrops are perfectly spherical, held in that shape by the cohesive force of surface tension. But as they grow larger, like the one our molecule is in, the pressure of the air pushing up from below flattens its bottom, while surface tension keeps its top rounded. It takes on the shape not of a teardrop as is often depicted, but of a tiny hamburger bun or a kidney bean. Our molecule inside this falling drop tumbles and oscillates as it descends, a tiny transparent world hurtling through the sky. The fall is a sensory rush. The landscape below, once a distant abstract map, grows larger and more detailed with every passing second. The green patchwork of the forest, the dark ribbon of a river, the grey scar of a rocky outcrop, all resolve into focus. The sound is the rush of the wind, the sound of its own passage through the air. It is a journey of a few thousand feet, a fall that might last several minutes, but it is a journey that bridges two worlds, the ethereal, atmospheric realm and the solid, terrestrial one. Finally, the moment of arrival. The raindrop containing our molecule makes contact. It doesn't land on a hard, impervious surface, but on the broad leaf of a fern growing on the forest floor. The impact is a soft splash, a tiny explosion. The raindrop shatters, its cohesive unity broken, its constituent molecules scattered across the waxy surface of the leaf. Our molecule now lies in a thin film of water, clinging to the green surface, reflecting the dappled light of the forest canopy. For a moment it rests, its long fall complete. Other drops are landing all around it, a gentle patter on the leaves, a sound that is the very definition of peace and renewal. This is the music of the rain. This gentle rain is a gift to the land. Its arrival is a moment of profound relief and replenishment for the ecosystem. The fern our molecule has landed on, like all plants, is thirsty. Some of the water on its leaf may be absorbed directly, but most will drip off, falling to the ground below. Our molecule joins a trickle of water that runs down the stem of the fern and drips onto the forest floor, landing on the rich, dark soil, the duff layer of decaying leaves and organic matter. Here, its work truly begins. The soil, dried by the sun and the wind, eagerly absorbs the water. Our molecule is drawn into the porous earth, beginning the process of infiltration we have seen before. But this time, we focus not on the deep journey to an aquifer, but on the immediate impact on the topsoil, the zone of life. The water replenishes the moisture that was lost to evaporation and transpiration. It fills the spaces between soil particles, making itself available to the vast, thirsty network of roots that permeates the ground. The trees, the shrubs, the ferns, the mosses, the entire plant community can now drink. The gentle rain has closed the loop that began with transpiration, returning the water that the forest itself had offered to the sky. The rain does more than just quench thirst. It is a cleanser. As our molecule fell through the atmosphere, the raindrop it was part of collected microscopic particles of dust, pollen and aerosols. This process, called washout, literally scrubs the air clean. When the rain reaches the forest, it washes the accumulated dust and pollutants from the leaves of the trees, allowing them to breathe and photosynthesize more efficiently. The air after a rain shower smells so fresh and clean partly because it is cleaner. Our molecule has been part of a planetary shower, purifying the very air that life depends on. The rain is also a courier of nutrients. As it percolates through the canopy and the soil, it dissolves essential nutrients that are locked in dead organic matter, like fallen leaves and decaying wood. It creates a nutrient-rich solution that can be readily absorbed by plant roots. It is a catalyst for decay and renewal, helping fungi and bacteria to break down the dead and release their components back into the circle of life. Our molecule might dissolve a molecule of nitrate or phosphate, carrying it directly to the root of a young sapling, providing the building blocks it needs to grow. The arrival of the rain triggers a burst of activity in the forest. Dormant spores of fungi and mosses are awakened. The earthworms and other invertebrates in the soil become more active, their tunnels aerating the soil and helping the water to penetrate more deeply. For many amphibians, like salamanders and frogs, the rain is a signal for movement and reproduction, their moist skin requiring a wet environment. The forest floor, which may have been quiet and dry just moments before, is now alive with movement, growth, and transformation. The gentle rain is a system-wide activation signal. Our molecule's journey continues. It may be drawn quickly into a root to begin the upward journey through a plant once more, or it may percolate deeper, past the root zone, to recharge the groundwater and the aquifer below, a slower path of renewal. Or it might join with other raindrops on the surface, forming a tiny rivulet that flows over the forest floor. This time it does not become a powerful erosive force. The forest floor, with its thick mat of leaves and roots, acts like a giant sponge. It absorbs the rainfall and slows the runoff, preventing the soil from being washed away. The water that does flow off is clear and filtered. Our molecule, as part of this gentle runoff, trickles into a small, clear-running stream. It flows through the stream, which is now slightly fuller and faster from the rain. It tumbles over mossy stones and past the shaded banks. The water is cool and rich in dissolved oxygen, a perfect habitat for fish and aquatic insects. The rain has not just replenished the land, it has refreshed the aquatic ecosystems as well. The stream flows into a larger river, and our molecule is once again part of a larger body of water, its journey as a single raindrop complete. Contemplating this journey, we see that rain is not just water falling from the sky. It is the culmination of a vast, complex process, and the beginning of another. It is a moment of connection, a physical link between the atmosphere and the biosphere. The gentle rain is a transfer of energy, a cleanser of the air, a courier of nutrients, and a trigger for life. It is a gift, the payment of a debt that the sky owes the land. Our molecule, in its fall from the cloud to the earth, has been a messenger of this gift. It has brought life, purity, and renewal. Its arrival was not an end, but a re-beginning, a reaffirmation of the eternal life-giving cycle that sustains the green mantle of our world.